now we can move to the next speaker, who is Dr. Tonelli Cueto. Josue, can you maybe share your slides while I present you? Maybe activate your microphone.
Yeah, let me go ahead.
So I met Josue, I believe it was in Leipzig. We were both PhD students back then in 2017. He was a student in Berlin, I was in Magdeburg. He's now a Rufus Isaac postdoctoral fellow at Johns Hopkins University. And he did his PhD thesis in Berlin with Peter Burgeser and Felipe Kucher on condition number in semi-algebraic geometry, and his research topics are numerical algorithms and condition-based complexity, computational algebraic geometry, and random geometry. Well, we cannot see your slides, I think.
Yeah, and on the process.
Oh, yeah. Okay. So
Is this?
we start. It's 6:36. So yeah, let's take into account the 6-minute shift. Well, 6:36 in Madrid. Sorry, it's.
Yeah. How many minutes do we have exactly?
So we have 30 minutes, including questions. So maybe 20, 25. I don't know if you want more questions, maybe 20 minutes. If you want less questions, maybe 25. Compute 30 minutes, including questions.
Yeah. So yeah, thanks a lot, Alexandru and Mir Hossein, for the chance to speak to you. Okay. So I will be talking about condition-based low-degree approximation of real polynomial systems. So maybe before I start in this, let me say the problem. So we have some real polynomial system, okay? Some polynomials of 1 fq equal to 0 in n variables. And now one of the things is, what can we say about the conditioning of this system? And then another one is, what does the condition say about the zero set? Okay, this is the part where I'm coming and looking at the condition number of this. So for continuing, we might wonder, okay, what's the condition of a polynomial? What is this conditioning? What is that thing that is highlighted in the slides? So the main spoiler is that in the complex world, conditioning only controls the separation of the zeros. This is kind of a well-known set of results in complex geometry. And then in the real world, conditioning controls also the size of the zero sets. This is essentially the main message of this talk. So let's start with conditioning. So essentially, one of the main things that we should realize is condition numbers depends on the metric that we use to measure. So this means how we measure errors, and the condition number depends on the encoding that we do of information. So essentially how we write the problem that we have at hand. So to make let's say a faster way of understanding this, let me do the presentation in the form of Demel and Renegar of the condition number. So you have some input space. Then inside this input space, we will have some set of ill-posed inputs. So these are inputs that in a certain way we cannot handle with a numerical algorithm, because an arbitrarily small error will change combinatorial properties of the problem that we are trying to solve. And then the condition number will just be like the inverse to the distance to this ill-posed set. That's essentially the conic framework of condition numbers. And then it happens that a lot of condition numbers, including, for example, the Turing condition number that you find in numerical linear algebra, is a particular case of this condition number. So it's kind of a pretty general definition. Okay. So I will focus on this setting, how it is done with the one norm setting. This could also be done with the Weil norm setting, but given the length of the talk, I will just focus in one of the cases, and the other one you can find, I think there is a preprint in Hall regarding this work. Okay, so let's start with the setup. Okay, we need to put how we measure the errors and what are the ways. So the first thing that we look is, or the space of polynomials will be all the polynomials in Here there is an error. This should start at x1, not at x0. So in n variables, x1, x2, xn, that you have a constant term in the polynomial and that the support is contained into some common support set A. Okay, and now we have n polynomials. Notice that there is an n outside this set. Then we will look at the zeros of these polynomials in the cube minus 1, 1 to the n. So we are looking in this very specific region. And for us, the ill-pose set will just be the set of polynomials that have a singular zero. Why is this set of polynomials, let's say, ill-pose? Essentially, if you have a singular zero, a small perturbation can make either that this zero disappears or that this zero turns into two zeros. So in a certain way, numerically, we cannot really even know if we will have an ill-pose set, as there will be errors unavoidable. We will not be able to tell whether this polynomial system have actually zeros or not, because a small perturbation, arbitrarily small perturbation, will kill the thing. Okay, now how we will measure this? This is why it's called one norm setting. We will measure this with the one norm. Okay, so first, variety of polynomials of fi equal to fi sub alpha x alpha. The summation of alpha is implicit. And here x alpha is used x1 to the alpha 1, x2 to the alpha 2, etc. So alpha here is like a vector. Okay, and then what we do is we take the sum of all the absolute value of the coefficients of each one of the polynomials in our system, and then we take the maximum of that. And that is the one norm of the polynomial. Okay, so once we have the definition, we go to what is the cubic condition number. That's just a way. And for this, we have like this, let's say, convoluted formula. C1 of f is the supremum of x in the cube, where we are looking for the zeros, of the one norm of f divided by the maximum of the valuation of f at x, infinity norm. So this means that we take the maximum component in absolute value. And then, let me this up. And then the inverse of the Jacobian multiplied by some normalization diagonal matrix that depends on the degrees. And we take of this the infinity to infinity operator norm. This means this is the operator norm induced by the infinity norm in the codomain and the infinity norm in the domain. Which, if you remember properly, this is just the maximum of the sum of the absolute values of the rows. So in each row, you add the absolute values and then you take this maximum. And now you take the inverse of this. So this is the condition number that we have. There it goes. And one of the things is we have a condition number theorem, which is approximately this condition number is roughly the norm of f1 divided by the distance of f to the ill-pose set. So essentially it's a condition number in the sense that I said before. Notice that this condition number is infinity if and only if we have a singular zero in I to the n. Because if we have a singular zero, then f of x is zero, so its infinity norm is zero. And then the Jacobian will be singular, so the inverse of the inverse, all that quantity will be zero, and then we are done. We are dividing by zero, and then since this is a positive quantity, we take as infinity the convention. Okay. So now we go main theorem, simple form. What's the name? We take here the cardinality of set f, so the number of zeros, real zeros that we have in I to the n in this cube is bounded by some polynomial in n to the n. Okay, this is something that depends on the ambient dimension. And now the most important thing is log d to the n, so essentially a power of it, and then log n of the condition number. So it depends polylogarithmically on the condition number, polylogarithmically on the degree, and exponentially on the number of variables. This is the main form of the theorem. This is the main idea that we see. This is in a certain way telling us the condition number, the real condition number, so C1 of F, actually controls the number of real zeros that we have. And this is surprising because in the complex case, this does not happen. Now let's go and see the complex form of this theorem. By complex form, I don't mean over the complex numbers, but with more detail. So we have a partition of the cube into small cubes, and actually these cubes are pretty explicit. We start with a big central cube, and then we start putting rectangles. So the nearer that we are of the boundary, the more rectangularly will be the thing. Like this, shorter it will be in that direction. And then the thing is, this cover is quite small. It only has a size that is polylogarithmic on the degree, and this is fixed. Here I want to point that this does not depend on your polynomial at all. Your polynomial, this is independent of the polynomial system. And then for every b and every polynomial that we have, I think here this is this will be p of a, not hd. We have some approximation polynomial, phi of bf. So this is a polynomial system that approximates the original polynomial that is of degree bounded by a polynomial in n, logarithm of the degree, and logarithm of the condition number, such that the number of zeros of f in b is bounded by the number of zeros of this approximate low degree approximation of the polynomial. And even more, for any zero that I take of this of my original polynomial, there is some zero of this low degree approximation such that the Newton's method converts quadratically to it. So notice that this proof is almost purely constructive. The cover that I'm obtaining, the partition does not depend on the polynomial at hand. You can choose it a priori. And this is what is saying that in each one of the pieces of the cover, I have a low degree approximation that if I solve this low degree approximation and then using Newton's method, I can get the approximation of the zeros of my original polynomial system. Of course, notice that the catch here is that the degree that I need to get this low degree approximation depends on the condition number. And this will be important to what I say later. But now let's focus on some of the consequences of this. On the one hand, we have that if the size, if we have too many zeros inside the cube, then we have that the condition number is enormous. And if it is enormous, it means that a small error will make the thing change. The number of zeros change. So in other words, real systems with many zeros are badly conditioned, independent of whether how you do them. Then corollary 2, you take some random polynomial, and these are the hypotheses. So one is that when I evaluate Fix, they are independent, sub-Gaussian, and with anti-concentration. This is the assumption. And then when I look at the expectation of the number of zeros to the L, and now all of it to the 1 over L, this is a form of the L moment of the number of zeros as a random variable. Then this is bounded by the polylogarithmically on the degree, exponential in n, and then we have this L to the n. This is just telling us that our bound is sub-exponential. So a faster way of saying, okay, under very general hypothesis, this quantity is sub-exponential with constant log square of 2d poly n. So it's a pretty good, let's say, bound in a certain way. Then what means to be sub-exponential? It means that this random variable being greater than t goes down with an exponential tail. That is what it means. So essentially, having it many zeros is something rare. So now I will focus on a certain detail that I think is important to understand a little bit how this proof works and how everything that happens in this construction is kind of explicit. So if we look at the Smale alpha theory, so this is a way of telling whether or not Newton's method converts or not. So we start with an alpha that is just the product of beta and gamma, okay? Nothing special here. Now we start with beta, which is the norm of the Jacobian inverse multiplied by f of x. That is precisely the length of the Newton's method. So that's the distance between x and the Newton method of one iteration applied to x. And that is that difference. So this is what I was saying. We take x, we subtract the Newton's method, and then we get this long. So beta in a certain way is the size of the first Newton step. And then we have gamma, which is a kind of a regularity. This is always have a horrible formula. We have maximum of 1. Then we put all these supremums of the inverse of the Jacobian, multiply by the higher order derivatives. Then with this weird exponent that is 1 over k minus 1. And this is how it goes. And why we care about this is Smale's alpha theorem, which tells us that there is an absolute alpha star greater than 0, such that if alpha is less than alpha star, then the Newton method at x converges quadratically. And quadratically means fast. It means that at each iteration of the Newton's method, we gain double the digits that we used to have. Like if you initially have 5 digits of precision, then in one step you will have 10 digits of precision. Then in the next one you will have 20 digits of precision, and so on. So essentially, you are multiplying by 2 the precision that you have, the number of exact digits of your solution that you have as you apply the Newton's method. This is another way of expressing it, but okay. Okay, why I'm putting all this is for speaking about the truncation theorem to show a little bit that the low degree approximation that we use is something that is very explicit. So you take your favorite polynomial, delta, whatever. Then we define this truncation parameter. It's kind of similar to gamma, but okay, this forms from the, essentially this follows a little bit from the proof. Okay, and now the way in which I will truncate is I will take f sub delta, which means I develop the Taylor series of this up to degree delta. That is what f sub bar delta. And on the right is a way of writing this formula. I'm just doing this centered at 0, but this is just the Taylor expansion of f at 0 evaluated up to degree delta. And the main theorem, what it tells us is that if delta minus logarithm of delta plus 2, I mean this weird quantity, is greater than the logarithm of this tfx delta, okay, if this thing happens, so essentially if our delta is large enough, so essentially of the order of the logarithmic, then the alpha of f delta x is bounded by this quantity. And in this quantity, the only thing that we really need to pay a lot of attention is, on the one hand, is the 2 alpha f of x, and then that there is the gamma somewhere multiplying the t, and that then delta appears. And then here, the important thing of this is that this is telling us that if you have an approximate 0 of f a la Smale, so a la Smale means that the Newton's method converges quadratically. This is a very, let's say, succinct way of saying that. Then you have an approximate 0 of f delta also a la Smale. So if the Newton's method converges at some point quadratically to a 0 of f, then the corresponding Newton's method will also converge to a 0 quadratically of the low degree approximation. And we also have the reverse and more inequalities. So we can also have the opposite. If you have an approximate 0 of the truncation where the Newton's method converges quadratically, you also have the inverse. You have an approximate 0 of f that converges quadratically to a 0 of f using Newton's method. Okay, so now let me put a little bit on future work. So it's one of the first questions that we ask. Okay, we have an explicit method of truncation. We have an explicit way of constructing the cover. So why is this not an algorithm? This is the main question. And the main issue is that in order for this construction to become algorithmic, you need to estimate the condition number. And estimating the condition number is an expensive process. So essentially, since we cannot estimate fast the condition number, the algorithm that I given doesn't turn into efficient algorithm fast. Then another work that can be done here in another direction is to generalize this not only to zero-dimensional systems as I did, but also to positive dimensional systems. But that will require a lot more of effort. Because then we have to do either volume or Betty numbers, and this is hard in a certain way. And thanks a lot for your attention.
Thank you, Josue, for this talk in numerical algebraic geometry and condition number. Are there any talks? Any questions? Sorry, are there any questions from the audience? No, if not, then maybe I can ask. A question. So how far is this from being implemented? So you said that it's future work, but do you have already something, or is this just put for the future?
I mean, the issue is that to have an implementation that will work, you really need, what's the name? You need an estimation of the condition number, and this is something that we don't have.
Okay.
So essentially, the main issue here is that we don't have a way of, as of today, we don't know a way of estimating fast the condition number. And so even if you will get a fast estimation or implementation of this, we will not be able to do anything about it, because you will have a step that is incredibly expensive before you can even start computing the zeros.
Okay, and there's no promising no promise for the near future.
I mean, at least I hope that at some moment that there should be some achievement regarding it, but it's not something that is immediately obvious that is easy to do. Like, it's not something that you will go and say, oh, there is a clear path on how this can be done. Like, usually the thing that I think is that one should check the univariate case. After checking the univariate case, one should see if the techniques here can be applied to simplify problems where we have more structure that we can use. And maybe when we have more structure, you have that this extra structure that you have can be used to estimate the condition number in this subclass of problems.
There is a question on the chat. I think it's from Amir Hossein, right? Yes. Can you use some ML idea to approximate the to approximate the estimation condition?
I mean, I will say that the main issue with using, let's say, machine learning methods in this case is that the training data, you will use it for certain set of parameters, and then it will be very hard to generalize this to bigger parameters. Because imagine that you do this for polynomials of degree up to 20. First, you need to have the training set. To construct the training set, you need to use algorithms to solve the polynomials. This is one of the, I would say, hard things regarding this, unless one comes around a method to solve the polynomials to obtain the training set. But then, even if you have the training set and you train the method, then the main issue that you will have is that this is only up to degree 20. If then you want to solve polynomials of degree 50, you don't have trained methods, because finally you have expand the thing, and this is one of the difficult things still, like how when you have something that works from inputs of a certain size, how to make machine learning to learn something to inputs, numerical inputs and geometric inputs of a bigger size, like more higher dimensional methods.
And I don't know if is there any other question.
So maybe I add for the part that you said training something for a fixed size and then generalizing for a bigger size. We had something similar problem in CRM theory. We have a lot of reactions, and then we could use some of these methods such as support vector machine random forest that they are for fixed size because length of the features should be fixed. That was not good. We went try graph learning algorithms because that can have arbitrary number of nodes and edges. But then the question would be, what kind of graph you are going to use to represent these systems of equations? So yeah, I understand that.
More questions? If not, maybe I can ask something. It's just like a hint or like a very nice question. Is this somehow related to? Maybe it doesn't make sense, so please correct me. But is this somehow related to this de-randomization problem, or it has nothing to do?
No, this has nothing to do with the with the randomization problem. That's
Okay,
more
sorry.
related. That's more related when you have structure, arithmetic circuits and so on, and then you want to test if the circuit is zero or not.
Okay, sorry. And I mean, if so, let us forget about the difficulty of computing the condition number. Can you also going through what Amir Hossein said? Could you use this for parametric systems in what would be the use in parametric system coming from biochemistry? The degrees there are usually at most 2. You have many polynomials of degree at most 2 with lots of parameters. I don't know. Do you think it could be used in this field?
I mean, I think for the main issue with chemical reaction networks is that I think usually you have a lot bigger dimension, and what you really want to reduce is the dimension of the thing, because you have a lot of variables. It's one for each one of the concentrations of the molecules. Then you might not have extremely large degree, and then you want to get something that is able to go around the n. All the methods here, what they exploit is that the degree is large, number of variables is fixed, and then we turn down the degree. But when you have the opposite situation, the methods in this talk essentially are a little bit useless, because then you still get something that is exponential in n.